introduce Galia Dafni from Concordia University, and she will be giving the talk on BMO and variations.
Thank you, Nina, and I'd like to thank, oh wait, what happened? Thank Javad and Ilya and Damir for the invitation. And I'm going to be speaking about joint work with Almud Burchard at Toronto, Almaz Butayev and Ryan Jibara at Cincinnati, and it's separate. There's two sets of joint work there. So I'm going to try to put everything in this one talk. I'm sorry, some of you may have heard parts of it before, but I wanted to give a kind of overview of some things that I've been doing recently with my collaborators, and it's not really in the area of the workshop in analytic function spaces, but in fact, I think it's good to give an idea of what happens in the more real BMO case. And things are a lot less rigid than I think in the complex setting. That's my feeling. I don't know. I've always felt that, you know, it was more beautiful but more rigid in the complex setting. And in the real setting, we have a lot of freedom, and that's where the variations come in. Is that we can start with a simple definition, like the definition of BMO that you saw. So this is already, I put it in the context of Rn. So you saw it in the, on the circle, but things are gonna be different in Rn, especially when we deal with unbounded domains. And so you should already be familiar with this definition. And you notice that, so this symbol is just the average. And basically it's a very simple definition that involves integration, so measure. And where do we see the geometry? Oh, there's a chat. Do I have to, oh, you still see my title. Okay. Okay.
Sorry, my mic was off.
Yeah,
we see the title page, yeah.
Okay, so what should I do? So, okay, I think what I need to do is, okay, I can't get rid of the chat.
If you double click on it, it doesn't work.
Okay, so maybe I'll get rid of the full screen. I think the full screen is the problem.
Okay, we see it now. Yeah, it's the same.
Yeah, so okay, so let me, yeah, so okay, but now I have, for some reason, I have the chat there, the box. Okay, 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 so let me go back. Okay.
Yeah. Good luck with 124 pages.
What?
Good luck
no,
with 100.
No, I think it's the pauses. The pages count the pauses. Okay, let me get on with it. So sure. So you see that where the flexibility lies is that we have these two aspects. There's the integration aspect, and then there's the geometry is in the cubes. Okay, so that's where we're gonna see later that we're gonna do some variation with that. But first, let's look at the sort of measure aspect of it, and that's the okay, I still can't do anything. Okay, the John Nirenberg inequality that you also saw previously in the lectures in the mini course, and you know that it's an if and only if. So can you see the bottom of the screen? Yeah, because I don't see can you see it?
The last line says, oh yeah, now I think it's the full screen.
Yeah, okay, I can, yeah, okay. So, so it says that we can characterize BMO in terms of this distribution function on cubes. And that brings me to the first topic, which has to do with rearrangements. So we're going to define rearrangements using the distribution function. And I think everybody is familiar with that. So it's increasing and right continuous. And we will call the super level sets, we'll call them level sets. And we're going to assume for everything that we're going to do that this distribution function decays at infinity, goes to 0. And that allows us to define the decreasing or non-increasing rearrangement as essentially the inverse of the distribution function. So if you're not familiar with it, let me just show an example here. The way I think of it is, so here's your function on the left, and then you're basically you get a new function on the half line where the mass is pushed towards the y-axis. So you get a decreasing function, a monotone decreasing function, which is equimeasurable with your original function. So the measure of the level sets is the same. Okay. So there's another rearrangement. This time we're taking functions from Rn to functions on Rn. And basically we're doing the same thing. We're sort of pushing the mass towards the origin in a radially symmetric way. And so again, it's a radially decreasing function, which is equimeasurable with f. And we now want to know what happens to BMO under rearrangements. And if you are familiar with this, you know that LP is invariant under rearrangement. So if you have equimeasurability, the distribution functions are the same, then the LP norms are the same. If you just take some arbitrary equimeasurable rearrangement of BMO, then you won't get invariance. So if you take this function log, which is the typical function in BMO, just the log, but we are going to truncate it at plus or minus 1, and then we're going to shift it to the right, basically, and you will get well, it's kind of a shift and a redistribution of the mass. Then this one, because we're cutting it off on the interval 0 infinity, is not going to be in BMO, even though it has the same distribution function. And another problem that we can have is that we can have BMO functions that are not rearrangeable. So what it means is that their decreasing rearrangement is just a constant infinity, and we don't want that. So there's a few issues when dealing with rearrangements in BMO. There's also the issue I didn't mention here that BMO is taken modulo constants, but adding constants is not good for rearrangements because we're taking the rearrangement of the absolute value of the function. So it's you have to be careful, but there is an old result of Bennett-DeVore-Sharpley, which implies that the rearrangement is bounded on BMO with a constant of this order 2 to the n. However, an old result of Ivo Klemisch says that in one dimension, the constant is 1. So this brings the question, what is the best constant in this rearrangement inequality, and how does it depend on the dimension n? So the same questions about the boundedness can be asked for the symmetrization. And we know that in the Sobolev space, there is boundedness. And Clemish also looked at the symmetric decreasing rearrangement in dimension 1. So in dimension 1, it's just an even function around the origin. And he showed that you have a bound for that. But the boundedness in dimension bigger than 1, what is the result? And of course, another question is, what is the constant? So this is what we've been doing with Almut and Ryan, but okay, I guess I didn't finish with the question. So we have another question, which is the continuity, and that's separate from the boundedness question because these are nonlinear mappings, and continuity can fail. So even though you have continuity on the Sobolev space in one dimension, you don't have it in higher dimensions. So we also asked, is the decreasing rearrangement and the symmetrization, are these continuous operators in the BMO norm? So what I was saying before at the beginning is that there is some flexibility with BMO if you change shapes. And we want to ask what happens if we replace cubes by other shapes. And it seems that there is some improvement, not if we replace cubes by balls, because replacing cubes by balls gives you the same BMO shape, space. But if we replace cubes by rectangles, this is something that's in harmonic analysis. When we look at rectangles, usually things are worse because, for example, I think Sandra Pratt mentioned that the strong maximal function is worse than the regular Hardy-Little maximal function. But in this case, for these bounds on the decreasing rearrangement, if you look at something called strong BMO, or this is what Sandra called little BMO, and it's just taking the BMO, the mean oscillation over rectangles instead of cubes, then you get the same bound as the Clemish bound. You get a constant of 1 for the decreasing rearrangement. And this is because in some way, with the rectangles, you have the flexibility that you have in one dimension. So with Ryan, we, even before we started working on rearrangements, we had the idea that you can try to just define BMO in the most general setting. In fact, this is an RN, but we later had some work with a student, Andrew Levine, where we do it on measure spaces. And this is an idea that people have many people have in harmonic analysis to work on a basis of sets instead of using cubes or balls, but we call these sets shapes because we were thinking of changing the shape that we're working on. And so it's just the same definition. And surprisingly, a lot of the properties that you expect from BMO, like the completeness, can be proved in this general context. Completeness is basically the fact that it's a Banach space and is basically the connectedness of the domain, it turns out. So with this tool, this kind of changing of shapes, we want to try to get improved constants in the rearrangement inequality. And the key, if you look at the proof of Bennett-DeVore-Sharpley, and also for the John Ehrenberg inequality, these constants are coming from the Calderon-Zygmunt decomposition. And so if you can get a better decomposition, as you can in the case of dimension 1, you have the Riesz rising sun lemma, that's more precise, and that allows you to get the constant 1. And this is what Korenovsky did when he and Lerner and Stokoulis got a version of the rising sun lemma for rectangles. So we somehow want to exploit that. We want to exploit the fact that with rectangles, things are better. And so the first step was to get to just write down what a Calderon-Zygmunt decomposition means in this more general context. So for those of you who are familiar with the Calderon-Zygmunt decomposition, you can just see that these sets Si play the role of the cubes in the Calderon-Zygmunt decomposition, and the Si tilde play the role of the double of the cubes. And so in Rn, if you double a cube, the measure is going to get multiplied by 2 to the n. So C star is here 2 to the n for the classical Calderon-Zygmunt decomposition, but this is just a statement of what we would like. I'm not saying that this is, we're not proving this. This, by the way, appeared in the proceedings of the AMS just in the latest issue now. And then we say, if we have this Calderon-Zygmunt decomposition, then we have the boundedness of the decreasing rearrangement with the same constant. So what this result does is it really shows you that the constant can be taken directly from the Calderon-Zygmunt decomposition, this generalized Calderon-Zygmunt decomposition. And this can be done even in a more general context in measure spaces, okay? So that's what I said, that all this part is just measure. And the other part, the geometry, is where the shapes come in, and that's where you are, the challenge is to get the Calderon-Zygmunt decomposition with a good constant. And what we know is that the extreme case, the case of rectangles, or the one-dimensional case, you have the constant 1 from the rising sun lemma. So one wants to have a kind of intermediate case, which allows you, on the one hand, to get the good constant in the Calderon-Zygmunt decomposition, and on the other hand, be able to navigate between those shapes and the cubes, because ultimately we were interested in the constant for cubes. And arbitrary rectangles, you cannot go back to cubes because they have unbounded eccentricity. So you need a family of rectangles with bounded eccentricity. And so this is what we do. So in fact, this is the latest version of our work. In the original version, we found a family of rectangles that is closed under bisection. And the bisection property allows you to get the constant 2 in the Calderon-Zygmunt decomposition. And then you have to go from that family of rectangles to the original cubes. And very recently, we learned about a result of Wick, who used a special family of cubes to obtain improved constants in the John Nirenberg inequality. And when we replaced our original family of rectangles by this family of rectangles, we were able to improve the constant also to the square root of n. So it's a reduction from the exponential to the square root. And this false cubes is basically, you put together some, in some dimensions, your cube has side length 2 or 2 times s. And in the other dimensions, your cube has side length s. And when you bisect such a cube along the last side that has, the last dimension that has side length 2s, you end up with 2 false cubes with the m is reduced, but the m depends on the cube. There's no one fixed m. Each false cube has some m that you go to. And of course, if it has to be less than n, otherwise, if you reach n, it's just a cube of side length 2s. Okay, so this is where this is how we got these improved constants. Now we want to go back to the boundedness of the symmetric decreasing rearrangement and relate that rearrangement to the decreasing rearrangement, the one-dimensional one, with this inequality. And that gives us a bound which comes from the bound on the decreasing rearrangement. But then there's this annoying, extremely large constant n to the n over 2 times the measure of the ball, which comes from the following kind of exercise where the symmetric decreasing rearrangement works well with what we call polar rectangles. So they're just rectangles in polar coordinates. These are the red objects, and you can compare them to balls by taking inscribed and circumscribed balls. This is what I mean by comparing. I mean volume comparison. But you end up, and then for these polar rectangles, you can use the decreasing rearrangement, and you get from the symmetric decreasing to the decreasing rearrangement, you have this factor because you're going from one dimension to n dimensions. So these constants are just a result of how we're proving it, but it's still a bound which was not known before. It was not known that it was bounded. Okay, so I think that's all I want to talk about the boundedness, but we still have the question of the continuity. So what do we want to say about continuity? Well, first of all, there's the bad news, which is that it fails in BMO, but that was to be expected because we already saw that it fails in Sobolev spaces. So what is this picture telling us? On the left, you have the sequence of functions in blue, and these are the GK, and then F is the red function that's fixed. So you have the blue plus the red is our functions, and so if we look at the right-hand side, these are the decreasing rearrangements, and so since the GK go to 0 in the BMO norm, because if you look at this log, that has a constant BMO norm, but the 1 over K goes to 0. So the GK BMO norm goes to 0. then that means that the sum converges to F, and F is already decreasing, so F is its own rearrangement. But if we look at the difference of Fk star, so that's the GK, basically the F plus GK is Fk. We take its rearrangement and we compare it to F star. This will fail to converge in BMO because it has a jump of height 1 at t equals 1 here. So jumps, it's when you look at the oscillation of a function with a jump, it's always going to be bounded below by the half of the size of the jump. So how are we going to avoid jumps? That's really the question in proving continuity. And that's where we get to another variation of BMO, and that's VMO. So VMO, that you already saw also in the mini course, is the functions of vanishing mean oscillation. And here we're looking at what we call the modulus of mean oscillation is the supremum over all cubes of measure less than t. And that has to go to 0. And Saracen, as was mentioned in several of the talks, also on Monday in the contributed talks, Saracen showed that VMO is the closure. Well, it was discussed about the translations, but in the same result, he showed it's the closure of the uniformly continuous functions in BMO. So of course, not every uniformly continuous function is in BMO on the whole line. By the way, Saracen's result, it's often forgotten that Saracen actually proved his result on the line, not on the circle. So these are the typical functions in VMO. They're like not the log, but powers of the log. And you can also get discontinuous functions, but they cannot have jump discontinuities. So we want to exploit that by looking at VMO and monotonicity. And we have captured this fact in a lemma that says that if you have a monotone decreasing function on a half line or a finite interval, then F is in VMO if and only if it's continuous and it has this vanishing mean oscillation at the origin. So basically, for a monotone function, it's what you expect because the monotonicity means that the only discontinuities are jumps, and you can't have jumps because it's in VMO. And then the test for the vanishing mean oscillation is just at the origin. So you really have to look at the origin if you want to check the VMO condition. Now, we do the same trick. We replace the cubes by shapes, and we get a version of VMO on shapes. And we need a little bit more about the shapes. Actually, I think there's a typo. We need to assume that the shapes contain a differentiation basis, and we need this kind of density condition on the shape. So if you want, you can just imagine cubes or balls because those will satisfy by Lebesgue differentiation, they will satisfy this density condition. It basically means that you can always find small enough shapes such that if you have a set that a positive measure and its complement has positive measure, you can always find small enough shapes for which both the measure of the the density on the set and the density on its complement are bounded below. And what we can prove under these assumptions is that if you start with a VMO function, then the decreasing rearrangement is in fact in VMO. And that's basically a consequence of that lemma. And the first result says that the decreasing rearrangement of a function VMO is continuous, but to show that it's actually in VMO, remember we had to have that control at the origin, and for that you also need to assume the boundedness in the BMO norm. And we already know that that's true on Rn or on a cube. So for those situations, the classical situations, we know that the decreasing rearrangement takes VMO to VMO. Okay, so what about continuity? Well, we first have to assume the same hypothesis, this density condition and the boundedness on BMO. So here, this is, we just modified our result recently because we have a sequence of rearrangeable functions in BMO, and only the limit function has to be in VMO. So really, it's not about the sequence itself being in VMO, it's only about the limit function. And if the convergence is in the BMO norm and in L1, then you get that the decreasing rearrangements converge in the BMO norm. And this condition on L1 convergence, it's actually automatic in the case of a cube if you say assume that all the means are 1, because remember the mean oscillation over the whole cube is just if you subtract the mean and it's 1, then you get the L1 norm. So then it's 0. I'm sorry, the mean is 0. And so you get convergence of the rearrangements in the BMO norm. So I think that's all I want to say now about the rearrangements. There's also a corresponding continuity result for the symmetric decreasing rearrangements. Are there any questions about this part of the talk? Okay, so we're gonna switch gears a little bit and talk about another variation that one can make in the definition of BMO. It's basically BMO on domains. Now, it's actually the same variation that we started with, which is just taking a family of shapes. And in this case, it's just restricting to the cubes that lie inside a domain. In fact, we can even take it in an open set. And this was a definition made by Peter Jones in 1980. You look at the BMO on a domain, and if it's not a domain, if it's not connected, then instead of modding out by constants, you have to mod out by functions which are constant in each connected component. So it's a very natural definition. You have an embedding, the Sobolev embedding, and you also have this typical function, just like we have the log function on Rn or on the circle. If you look at the log of the distance to the boundary in the domain, that's the typical BMO function. Okay, so the basic question we want to address is the extension. If you have a BMO function in the domain, can you extend it boundedly to a BMO function outside on the whole space? And this question was already answered by Jones. And he characterized those domains for which you have extension in terms of a condition on the Whitney decomposition. And I don't want to say a lot about this condition. I'll just mention that it's connected with what is called the quasi-hyperbolic distance. And so you have these two distances in the domain that you can compute. One is measured along curves in the domain. So you integrate 1 over the distance to the boundary along curves in the domain. So you compute the shortest distance there. And the other one is sort of external to, I mean, it uses the Euclidean distance, the ambient distance. And it does have the distance to the boundary, but it's a sort of scaling factor. And the Jones condition is that the quasi-hyperbolic distance is controlled by this log distance. And if you, maybe some of you remember the talk of Alma's on Monday, then he discussed a lot more about these conditions. So what I want to say is just that, well, this is, I guess, the only part of my talk that's really related to complex analysis. So in the plane, this condition just means that the boundary is a quasi-circle, okay? But in higher dimensions, there is this characterization in terms of uniform domains. And these are domains where for every 2 points, you can connect them with something, with a curve which satisfies these conditions. So what are these conditions? Again, this was discussed by Alma's in his talk, but if you I don't know if I can draw. Okay, yeah, I can draw here. So you have a domain, and then you basically have between any 2 points, you can take a curve which where the distance to the boundary gets bigger. Sorry, this is not very good, but anyway, it's called a cigar, but it's more like a banana. So in the middle, it's going to be fattest, and then at the end points, it's going to be tapered. So this kind of curve, the curve inside is the center of this red banana. Okay, so that's the nature of a uniform domain, and a domain. The standard example of a non-uniform domain is the slit disk, because it violates this first condition. So the second condition is what's called a John domain, but we also need the first condition, which is essentially quasi-convexity. Okay, so the first thing we want to ask is what happens with BMO on a domain. If we change to VMO, does Jones' result still hold? Now, the reason it's not obvious is that the way Jones proved his result, again, using Whitney cubes, is that if you want to get the extension outside the domain, you sort of reflect into the domain, but you take the corresponding cube and take its average. So the Jones extension is a kind of step function outside the domain. So even if you're starting with a VMO function, which inside the domain, outside the domain, if you apply the Jones extension, you get a step function, and that is not in VMO because it has jumps. So that's one thing, that you cannot apply the Jones extension immediately. But the other question is, how do you even define VMO on a domain? Is it the vanishing mean oscillation condition of Saracen, which is this VMO1? Or is it the closure of the uniformly continuous functions in VMO that's equivalent on Rn, but do we know that it's equivalent in the domain? Or is it the closure of the continuous functions with compact support? So this is a space that's known as CMO. It was used by Koifman and Weiss, and in fact, the duality that between H1 and VMO, so H1 is the dual of VMO, in the unbounded case, it has to be CMO that is the pre-dual of H1. So it's not Saracen's VMO on the line, it's actually this CMO space. Actually, it goes back to Uchiyama if you want to find the original characterization of this space in terms of the vanishing mean oscillation conditions. Okay, so we have these three possible VMO spaces, and what we showed with the Almaz-Butayev is that we can have a single extension operator that extends BMO, VMO1, that's the one with the vanishing mean oscillation. VMO2 is the closure of the uniformly continuous functions, CMO, and Lipschitz functions. So all of these are the same extension, preserves these 5 spaces. And conversely, if you have an extension, a bounded linear extension from the smallest to the largest of these spaces, then you get that the domain is uniform. And this also just appeared in the Journal of Geometric Analysis. And the corollary, I haven't gotten to the corollary, so this is just a note about the norms, but the corollary is that the closure of the uniformly continuous functions is the same as the functions of vanishing mean oscillation if you have a uniform domain. And the proof of this extension result is just taking Jones extension and averaging it outside the domain. And it's averaged in such a way that you actually get a locally Lipschitz function. Okay, so just a word about this approximation result. Of course, the closure of the uniformly continuous functions is always has vanishing mean oscillation. And in the bounded case, all 3 VMO spaces are the same, but in a domain that is not bounded and is not a uniform domain like the slit plane, you can define a function that is the log going up on the top half plane and the log going down on the bottom half plane, a 0 in between. And it's easy to see that this is not going to be approximated by uniformly continuous functions. So this this is just a corollary of the extension result, this identification. Okay, now I think I have about 5 minutes left, so I'm going to talk finally about the final variation. And I realized when I wrote the title and abstract for my talk that there was a pun there. I wrote about it to Richard Fournier, who's not here today, but because he's a big expert on the Goldberg variations. But anyway, so I want to end with that, but I don't have any music to play for you. But anyway, this is the space known as BMO, lowercase BMO, and it's not the little BMO space that Sandra Pott was talking about. So this was defined by David Goldberg in 1979, and I prefer the term non-homogeneous. Some people call it localized or local, but for those of you, in complex analysis, you can think of an example of a function in this space. If you take just a BMO function on the circle or and extend it periodically on the line, that will be in this Goldberg's BMO. So it is local in the sense that it has this similarity to what you see on the circle, but it's not BMO localized. In fact, it's a smaller space. So it's not like when you take local LP loc, it's bigger than LP. So this is not local in that sense. And the non-homogeneous part comes from this fact that we're controlling the averages. So Sandra Pott talked about this control of the average for BMO on the circle. Well, you don't have that for big BMO on the whole space, but you do have it for this non-homogeneous BMO. And this is the dual of the local Hardy space. So Goldberg called these little HP spaces local Hardy spaces, and that's why the dual is called local BMO, but it's a little bit misleading. So the question is, well, first of all, I just wanted to say that this one here is sort of the scale. When we're in the non-homogeneous setting, we have to pick a scale, and the choice of one is the choice of scale, but we can change the one to any scale lambda, and the space is the same, but the norm is different. But when we go to a domain, it turns out that this scale lambda is very important. So the scale determines what we consider the small cubes and the large cubes. And on the large cubes, we have a much stricter condition. We control the averages. And if the domain doesn't contain any large cubes, then you're just back in the original BMO space. But even if it contains those large cubes, that's really not enough. So if you look at this domain, so I wanted to draw this quickly. So this domain is just here you have kind of a tube here, and then it opens up on the left. And of course, you could put arbitrarily large cubes in here. But if you look at the function, which is just x inside this strip, I think I mentioned earlier that no, I didn't mention it earlier, but anyway, the point is that if you look at the averages of this function, then if you take any lambda that's bigger than 1. So you can make you can control averages on cubes size bigger than 1, but you have no control over the cubes of size less than 1 in terms of averages. So this function can grow linearly. It will still be in BMO on the domain, but it cannot be in BMO on the whole space because the averages have to grow like logarithmically, not linearly. So this is the issue when defining BMO. So can I take like a couple more minutes?
Sure.
Yeah, I think so. We want to discuss extension domains for these little BMO, and we had the idea that these should be local versions of uniform domains. And in fact, Jones already defined such domains. They're called epsilon delta domains. And I'm not going to go through the definition because, again, this was done by Almas on Monday, no, not Monday, it was Tuesday, sorry, his talk. And if you're on a bounded domain, it's the same as uniform. But the strip is an example of an unbounded domain, which is not a uniform domain, because remember that condition, the one with the cigars would have to become very, very thin as you go further out in the strip. So these epsilon delta domains were already proved to be extension domains, but it wasn't an if and only if. So only in dimension 2 is it an if and only if. But in general, you can extend. Jones showed that you can extend Sobolev spaces from epsilon delta domains, but if you can have extension domains which are not epsilon delta. And the question was, what is the characterization of these epsilon domains as extension domains in higher dimensions? And this is where we go to the zero smoothness, because this result of Jones was extended also to fractional Sobolev spaces. So you can let the smoothness go to 0, and zero smoothness is exactly BMO and VMO. So we have the following result. The following are equivalent. So the first two conditions were discussed by Almas because you can show that the epsilon delta is just a version of a local version of uniform domains. And he also discussed this condition. This is the condition on the quasi-hyperbolic convexity, quasi-hyperbolic distance. And the final condition that's equivalent to these is the extension, that there is an extension operator from this BMO space, BMO lambda to BMO for sufficiently small lambda. So once you have this result, you have a scale and you can define your BMO space. So you know what is the correct scale. And that's because the local the epsilon delta condition, this delta gives you the scale. And there's finally, again, VMO results. We have the approximation by uniformly continuous functions is equivalent to the vanishing mean oscillation. This is true also for other domains. For bounded domains without any restrictions, it was proved by Brzezis-Nierenberg. And we have the analog of the homogeneous result for VMO. So yeah, okay, so I think that's it.
Okay, thank you very much, Galia. Thank you. Any questions? just go ahead and ask if you have one. Okay, well, if there are no questions, let's thank Galia one more time. Thank you. And that concludes today's session. Tomorrow there is a seminar talk by Ronald Koifman at 11 o'clock. So see you all tomorrow. Okay.